Hello everyone, this is me and Ashmitha from Meta. Today we will share our recent experiences in improving network communication debuggability and performance observability in our large-scale training. So let me do the introduction first. My name is Min. I'm from AI System Core Design from Meta. My work is to focus on high-performance communication library in software with model core design. Let's first take a look at where we stand as network operation in our large-scale training. A typical large language model training often involves more than thousands of times of collective communication during every training iteration. This is the synchronization we have to pay to coordinate with every GPU when they are running fasted for computation. The exposed communication cost between those GPUs can even occupy more than 13% of our training execution time. That's a lot. And as a network team, we have the big mission is to push our network run at full speed, always, to reduce this communication cost as much as possible. While network runs fast, on the other hand, if any hardware fault happens during the network, unfortunately, the job often has to crash, and the consequent checkpoint restart. Let's say in our previous Llama 3 training, now we can share about that, is more than 20 minutes. That means the full system that involves tens of thousands of GPUs has to be idle, completely idle during that time. That's a lot, very expensive operational cost. So as a network team, we have the mission to make sure the network functionality is always very reliable. We reduce the restart as much as possible, and also when it's run stable, it's at full speed. Meta has started hosting high-performance computing style training system since 2020. In our training cluster, we consist of mostly thousands number of GPUs connected with high-speed Rocky network. And the production workloads we maintain daily, the most important one, as we well know, the ads recommendation model. And this workload is at 100 GPU scale, not very large. And our team has even innovated a lot of automatic tooling to allow us maintain the reliability and the performance of network very efficiently for those 100 scale GPUs workloads. For example, we have automatic tool to scan the machine health status when we are scheduling a workload onto a set of machine before it runs. Also, when it's starting running, we automatically collect the log from every software component during the training, and when any failure happens, we allow network engineer to go in there and use this collected log and metrics to root cause it. This approach worked fine for our classical 100 GPU scale workloads. However, since last summer, we started bringing up our large-scale language model training. This set of workloads can scale from several hundreds number of GPUs all the way to tens of thousands GPUs. And we found that there were a lot of operational challenge. The traditional routing no longer works sufficiently. In a nutshell, we have identified a number of new operational challenges when we are bringing up large-scale training in Meta. And I will not go into very much detail of each of them, but just to say, overall speaking, it's not only because of this increased scale of the system and the network, but also because we are involving more software components in our training stack. It increases the complexity significantly for our engineer to understand the correlation between stack and what happens. So next, I will bring back my partner Ashmitha to bring us into the detail of the performance part.
Thanks, Min. Hi, everyone. I'm Ashmitha Shetty, and I'm a network engineer at Meta. And my area of focus is to build tools to debug and optimize performance for large AI scale models. So before we dig into the observability stack that we built, let's talk about the anatomy of a large job training regression. So when a model developer reports that less number of tokens are being processed than expected, one of the questions that we network engineers get asked is communication the reason for the slowdown? If network indeed is the root cause for the slowdown, then we also need to know why it happens. Is it because of a slow endpoint due to a slow PCI connection issue, or is it the network medium itself slow due to bad routing or packet drops? So why is this a hard problem to solve? We have a few reasons for this. First of all, the complexity of our software-hardware systems. We have multiple hardware components and software layers of abstraction which have tight dependencies on each other. So this makes it challenging to know if compute or network is the reason for the slowdown. Secondly, our existing monitoring tools do not give us a model-aware network performance signal. We have metrics like timeouts and packet drops, which are a clear indication of something is wrong in the network. But there are other secondary metrics like ECNs, which do not always indicate a problem, but in certain scenarios can have significant performance degradation. So just looking at these standalone metrics without having the job context information, we cannot localize the impact of network errors or slowness to specific ranks or even know which exact communication stage was impacted. Third issue is the bad hardware detection. Sometimes we have bad software or hardware issues in our infrastructure that can remain undetected or take longer to detect, which can delay the training of the model. For instance, we had seen an issue where a bad switch image increased our packet forwarding latency, which resulted in about 20% of performance degradation. So failure to diagnose such problems and have proper signaling can lead to the training process continue under suboptimal conditions, ultimately leading to poor model performance. And lastly, we have the scale of our infrastructure. Our hardware metrics generate too huge volume of data when operating on thousands of GPU scales, which makes it impractical for manual triaging. So what do we need to build in order to solve this problem? So thinking at a high level, a collective is nothing but a series of data exchanges between the GPUs that are operating in an operation. So a collective is said to be performant when all these data exchanges happen within the expected cadence and speed. So we can tell if a collective is slow if any of these exchanges start late or takes too long. So one of the ways we can get this information is by instrumenting the application stack. So what's the best layer to add this instrumentation? So our training stack is pretty complex and has many layers of software abstraction. So when we think about the right layer to add this abstraction, I think the collective communication library stands out. The reason being the collective library is designed in such a way that it can abstract the network transport from the high-level machine-level framework. So now that we know what to build and where to build this, let's look at the solution. So our solution is to have a generic real-time network tracing integrated in MetaZone custom communication library called as NickleX. So with our custom-built library, we can now translate the high-level training communication request to our low-level transport operations. This has allowed us to build a more collective and model-aware network performance tracing. It also gives us the flexibility to add tracing which is more tailored to our needs. We can choose what events to track, how to format the data, and store these logs. By analyzing the trace data, we can identify where the training process is slow or inefficient and make changes to improve the performance. Also, since it's custom built, it makes it easy to integrate with some of the tools and libraries in our existing infrastructure. So now that we've talked about the design, let's look at some of the applications of this tool we built. So before we do that, how did we identify slow ranks in the past? In this particular example, we have 4 servers with 8 GPUs communicating each other in a rail-based manner. So when one of the NICs slowed down due to maybe a slow PCI issue, we were able to detect this slowness in the receive direction using PFC counters. However, if the sender itself is slow, we have no metrics to know about this slowdown, which means we cannot even know if the GPUs are even pushing the network hard enough to begin with. So how does the new solution that we built fare in debugging this problem? With the custom profiling layer that we integrated in NickleX, we now have access to each work request level information, like the wiki size, the time it was posted, and when it was completed. So the slow rank detection module that we built on top of this profiler can use this information to aggregate the latencies of the completed work request in a given window of time and compute the average bandwidth for every rank pair in the job. Looking at the result of the observed bandwidths for the PCI slowdown example in the previous slide, we see visible slowdown for all the communications involving the slow host. We can similarly extend this approach to root cause any slow communications due to network and not just the slow endpoints. So we just spent the last minutes talking about the performance profiler that we built to root cause any slow ranks or slow network, but how do we know if a slow network is actually causing a model degradation? So for that, we need to understand what is exposed communications. A training iteration is nothing but consists of communications and computation operations. If the communication operation is happening at the same time as the compute, then any slowdown in the communication is not going to result in a model degradation. But if the compute is actually waiting for the previous communication to finish, then any slowness in this communication is going to directly impact the model performance. In this particular example that you're seeing, the collective 1 is largely exposed, whereas collective 2 overlaps with compute, so any slowness in collective 2 is not going to impact the job. So in this showcase, we show how we combine the 3 visualizations that we built in order to complete this debug workflow. First is the model performance timeline. This basically tells us if there's regression in how fast the model is consuming the tokens to train. Secondly, we have the detailed breakdown of the parallelisms and the communication operation times. This tells us the most exposed communication times that are very sensitive to the model performance. And third is the performance profiler that we already visited, which basically tells us if there's any slow ranks or slow network. So we talked about using this workflow to identify performance regressions, but we can use this similar logic to identify any performance optimization opportunities. For example, if we identify the FSDP parallelism is more exposed, then we can actually spend time tuning collectives like all gather and reduce scatter instead of other collectives. So now that we've talked about how we solve performance regression for large-scale training, I'm going to hand it over to Min, who's going to talk about how we debug jobs, training failures in large-scale jobs. Thank you.
Thank you, Ashmitha. Hopefully everyone has enjoyed the experiences we shared in performance. Now let's shift the topic a little bit and take a look at how we handle failures. The typical network failure debugging flow is very similar to performance regression. We monitor the system and observe any symptom happens and involve the analysis based on this observed symptom. The most commonly observed failure symptom is stacking application or network timeout, which means during the training we found that there are a set of processes or all processes starting hanging, not moving forward from some point. And the root cause of such kind of stuckness, many times it's not actually because of network, it's because of the software stack, like a invalid user program that does not synchronize between GPUs correctly, or it may be because of a hardware failure, maybe in GPU or in network adapter or in the switch. And as a network operational engineer, the goal is to quickly root cause and identify the root cause and mitigate or fix it as soon as possible to allow the application to restart. We use, as we mentioned before, also I think Ashmitha shared the challenge we had in performance regression debugging. It's very much impractical for engineer to use traditional manual triaging based on machine matrices or per process logging to identify the cause, just because it's a huge amount of data we collected in large-scale training. And most of the information are just noisy, not anything related to the failure itself. Maybe someone may ask, let's just take more time to digest this large data. But the downside is that if we take more time to root cause fix it, which means that's a huge cost we have to pay. We either have to let the full system, which is tens of thousands GPU, idle during day and night, Or we just say, we just try to remove some potential bad machine, rerun it, and that would cause tens of thousands GPU to boost up for maybe 20 minutes just to prepare for the first training iteration. That will give us a very expensive power bill. So all of those challenges and the potential cost motivated us to revisit our final debugging routine and improve it. Similar to the improvement we made in performance observability, we also built a semi-online failure localization system. This mostly involves a tightly integrated instrumentation module in our training stack. We host it in the NicoX communication library. Here we can track the collective communication happens on every rank and the correlation between the model level, let's say training iteration, and also the underlying individual network operation. We trace this useful information and store them in CPU memory. It's very lightweight. And we quickly dump them to our file system. When any failure or stuckness happen, the engineer can go and use this information to try engine. And also it's not manual. We build an expert knowledge guided script to automatically scan all of those critical information and tell us the root causing pair of processes. As we mentioned, the most commonly happen trouble is one, either invalid user program, that's a software problem, or a hardware, broken hardware. In the next two slides, I want to go through this semi-online failure localization system, and by using two of those examples. Let's first look at the example that caused by hardware fault. Here we show a picture that identifies a typical three-dimensional parallel training in our Llama 3 model. You can see there's just several dozen of GPUs, but in real case, you can image this is several thousands GPUs, and there are three ongoing collective happening just for every single GPU. In this example, the x-axis shows the tensor parallel altogether that's ongoing and it's stuck. Meanwhile, it also involves a y-axis pipeline partition send receive. And on the third dimension, it also have a fully sharded data parallel altogether ongoing. Let's say the root cause of this full system stuckness is because of two processes on the third dimension, as we labeled as red, because of the interconnect switch has a flip issue that caused the FSDP altogether stack. That's the root cause, and the way we use our system to automatically identify the root cause is to collect the last active network operation on all of those ongoing collective. Then we can compare which collective start seeing this stack first by comparing the last active net operation time point. We can use this to quickly identify. Now we know those two processes in the FSDP altogether is the first one getting stuck, and all the other ranks are stuck just because of the cascading scenario. And the entire process is just a couple of minutes for us to get this root causing pair. And in addition, this system also allowed us to generate an independency graph that can explain to engineers why we have two ranks stuck and caused the full system stuck with different collective. The next example, we want to show a software bug. The previous hardware fault is a commonly happen issue during the training in months that after the model frozen. But many times we often have this trouble when we are in active model development stage or in fine-tuning stage. This example is actually a real use case so we get resolved in our previous Llama 3 405 billion model fine-tuning. The model developer was fine-tuning the model for vision, and the job gets stuck with thousands of GPUs. The traditional approach cannot help much. It may take like tens of hours without getting this problem identified. Using the new system we built, we automatically collect the start and end time of each rank in every collective. And then we compare if we see all rank has joined the collective. If we find any rank not a start or just not even getting scheduled for this collective, now we know, okay, that particular rank has a problem because it does not join the collective and cause all the other rank in that collective just wait for that forever and eventually hit timeout. Then it allows the engineer or developer to just zoom into that particular rank and check the more detailed logs, maybe from other component or from hardware matrices. This allowed us to quickly identify the root causing rank and mitigate, resolve the problem. Now here is a super bug, also in a couple minutes. All right, I think we have shared a lot about our final debugging as well as performance debugging. I think next Ashmitha will help us conclude this talk.
Thanks, Min. So to conclude, the three main key takeaways are: network reliability is foundational for our large-scale training. A reliable network ensures that we can operate our systems effectively and efficiently. Secondly, as our models and infrastructure continues to grow in scale and complexity, it's important to have innovative tools that can keep up with this scale. Lastly, we have observed that having independent network metrics that track and maintain our system health are necessary, but it's not sufficient when it comes to debugging performance issues for large jobs. For this reason, we added instrumentation in our application stack to give us much more precise and low-cost observability and debuggability in real time. Some of the ongoing and future work in this area are: first, we are still continuing to build a more holistic and end-to-end online automation system that can not only detect these anomalies, but can quickly alert, recover, and mitigate these issues while having minimal impact to our production jobs. Secondly, we have a rich set of hardware signals in our infrastructure. We are looking at ways to integrate these signals to give us a much more comprehensive understanding of the failures. Lastly, with all the detailed tracing that we have enabled in our communication library stack, we have a lot of signals at our disposal, but we are looking at some core signals that can actually inform future pathfinding efforts. Overall, the opportunities in this space to improve performance are a lot, and they're not just nice to haves, but it's very important when it comes to when we scale these jobs to thousands of GPUs. Thank you all for listening, and looking forward to take questions in the end of the section. Yeah.